Bismillahirrahmanirrahim. In this video we are going to discuss that how we can represent a three-phase system in terms of space vector. Okay, let's suppose that we have a system of two axes which are drawn like this. Okay, so let's suppose that this is axis D and this is axis Q. You can give it any name, x-axis or y-axis. And now we suppose that our three-phase system is distributed in this space. This is our phase A, this is our phase B, let's suppose, and this one is our phase C. Okay, so let's suppose that phase A is making angle theta with this d-axis. Then phase B will be at the angle of 2 pi by 3 from our phase A, and phase C will be at the angle of 2 pi by 3 from phase B. So in a balanced three-phase system, all of these are at the angle of 2 pi by 3 with respect to each other. Now if I take the projection of this phase A along d-axis, so that will be this component, and if I take the projection of phase A along q-axis, so this will be the q component. So we can take the projection of phase A on D and Q axis. Similarly, we can take the projection of phase B along D and the Q axis. So now let's draw the negative part of this D axis as well. This D axis is continued like this. This is minus D. This you can see plus D. And if I sketch the Q part, negative Q part, that will be like this. Okay. So the component of phase B along the D axis will be negative in this orientation, and the component of phase B along Q axis will be positive. Similarly, we can decompose any quantity along the C axis or the C phase in D and Q axis part. Okay. So how we can find out the components of phase A along with D and the Q axis? We are going to take the projection, and for that we will have to multiply any quantity which is along the phase A line with e raised power j theta. Okay, so e raised power j theta is basically equal to cos of theta plus j sine of theta. So if I want to take the projection of phase A along D and Q axis, so the real part will be whatever is the quantity along this of this phase A multiplied by cos of theta, you will get the component along D axis, and the quantity along this A axis multiplied by sine of theta, where this is the angle theta, you will get its projection over the Q axis. So basically we can say that its position vector is E j theta. When you are going to multiply the quantity along this axis of phase A, you will get its projection over the D and Q axis. Similarly, anything that will be over here along the B axis, when you are going to multiply it with e raised power j theta plus 2 pi by 3, you will get its component along D and the Q axis. Similarly, the quantity over the C axis when multiplied with e raised power j theta plus 4 pi by 3, you will get its component along D and Q axis. Okay, so now I am going to draw these set of axes, phase A, B and C again over here. Let's suppose phase A is over here, and phase B is somewhere over here, and phase C is somewhere over here. So now I am going to assume that the phase A quantity is basically varying along this axis. This is the axis of phase A. I am going to call it axis. And if we have the three-phase balance system, so let me draw the waveforms for the three-phase balance system over here. Let's suppose this is our phase A, right, and the phase B is at the angle of 120 degree with respect to this, and phase C is further displaced by the angle of 120 degree. So I can write somewhat like this. Okay, so phase A is varying. So when it is varying along this axis. So in a one cycle of the phase A, it completes its variation along this axis. Similarly, phase B will be varying along this axis. The negative axis of phase B can be sketched over here, negative part of phase B. So this is B axis, which is at the angle of 2 pi by 3 from the phase A, and the phase C is varying along this axis. So this will be over here. So there is a time variation along these axes. So these are varying over here along this axis. Similarly, there is a time variation along this axis. There is a time variation along the phase C. So when multiplied with this position vector e raised to power j theta, you will get its d and q component. Similarly, when you are going to multiply any quantity along phase B with e raised to power j theta plus 2 pi by 3, you will get its projection over the d and q axis. Similarly, any quantity along the c axis, when multiplied with e raised to power j into theta plus 4 pi by 3, you will get its projection over the d and q axis. Okay, so now let's write down the expression that what will be the resultant d component and what will be the resultant q component, because if you know that one, you can define that position in the form of vector over here. So let's suppose that phase A has certain d component, phase B has certain d component, phase C has certain d component. So if I sum them together, I get something like that. Let's suppose this is the d and net, where d net is equal to d component of all of these phases, and this is the corresponding q net. So this will be the point that will be the resultant of these three variation phase A, B and C in the dq plane. Dq plane will also be called the space vector plane by me. Okay, so now if we decompose all of these phases into the components and we sum them together, we will get the resultant vector. So let's suppose that QR is the resultant vector, and that is basically equal to QD net QD component plus J net QQ. Q is the capital Q is representing any quantity, that may be the voltage, that may be current, that may be the flux, that may be the magnetic field, something that is varying. So that net point over here will be having two properties. One is the D value and the other one is the Q value, Q axis value. Okay, so the resultant QD is basically the QA plus QB plus QC represented along the D axis. Phase A component along D axis, phase B component along D axis, and phase C component along D axis. And the net QQ, net Q axis component will be the QA along Q axis, QB along Q axis, and QC along Q axis. Okay. So now let's calculate that one. At any instant of time, QA will be having certain value, multiply by cos of theta, that is this one, and we are basically taking this projection, sorry, this is cos of theta, this part along the d axis. So QA into cos of theta will give us the projection of phase A along the d axis, then QB into cos of theta plus 2 pi by 3, that will give us the projection of phase B along d axis, and then QC into cos of theta plus 4 pi by 3 will give us the projection of phase phase C along the d-axis. Similarly, the net projection along the q-axis over here, that can be calculated like this. This is QA into sine of theta plus QB into sine of theta plus 2 pi by 3 plus QCT into sine of theta plus 4 pi by 3. And then with the help of these two, we can write down the resultant vector. Okay, so QR, the resultant vector, can be written as like that. That is QAT. If you look at these two part, this one, sorry, this part and this part, if we are going to sum them and considering the q-axis as the imaginary axis, so I can write it like that, this is e raised power j theta, then plus QBT and plus QCT. So QBT will be multiplied with e raised power j theta plus 2 pi by 3, that's the position vector of phase B, and QC will be multiplied with e raised power j theta plus 4 pi by 3, that you can observe over here. This is basically going to make e raised power j theta plus 2 pi by 3, and this part along with this is going to be written as e raised power j theta plus 4 pi by 3. So I can write the resultant vector like this. Okay, so I can also write it in the matrix form like that, QD and QQ, that will be equal to cos of theta sine of theta. This will be cos of theta plus 2 pi by 3. This is sine of theta plus 2 pi by 3. This is cos of theta plus 4 pi by 3. This is sine of theta plus 4 pi by 3 into instantaneous value of phase A, B, instantaneous value of phase B, and QC, that's the instantaneous value of the phase C. So I can represent this QD and QQ like this with the help of this set of equations. Okay, for the sake of simplicity, I am going to assume that theta is equal to 0. So if the theta is 0, what that means, that our phase A is aligned with the d-axis. So let me draw those set of axes again over here. Let's suppose this is d-axis, this one is the q-axis, and if the theta is 0, it means phase A is aligned over here, phase B is at the angle of 120 degree from here, and then phase C will be represented over here. The phases will be at the angle of 120 degree, but the starting angle, the theta, if I explain it from this point, this theta is now become 0. That's why your phase A is aligned with the d-axis. Okay, so for this particular case, I can write down the equation like that QR, that is equal to, from this equation I can take e raised power j theta common out, and this will be QAT plus QBT into e raised power j 2 pi by 3 plus QCT into e raised power j 4 pi by 3. And as we are going to take theta is equal to 0, so e raised power 0 will be equal to 1. So our resultant vector will be simply QAT plus QBT e raised power j 2 pi by 3 plus QCT into e raised power j 4 pi by 3. We usually represent e raised power j 2 pi by 3 with A. So if we consider it equal to A, and if we take the square on both sides, so I can write e j 4 pi by 3 will be equal to A square. So I can write this equation like this, that QR is equal to QAT plus A into QBT plus A square into QCT, where A is the unit vector J2 pi by 3 and A square is the another unit vector, that is J4 pi by 3. Okay, so we can also write down the values for e raised power j 2 pi by 3. This is basically equal to cos of 2 pi by 3 plus j sine of 2 pi by 3. So this can be written as minus 1 by 2 plus under root 3 by 2j. And if we look at this e raised power j 4 pi by 3, this is equal to cos of 4 pi by 3 plus j sine of 4 pi by 3. So this is equal to minus 1 by 2 minus under root 3 by 2j. Okay, so these are the unit vectors. Okay, now using this expression, I can write QD and QQ. These are the components of this QR. So I can write it in terms of matrix form like that, that this is cos of 0, sine of 0, then cos of 2 pi by 3, then cos of 4 pi by 3, sine of 2 pi by 3, sine of 4 pi by 3 into QA, QB and QC. Right? Now simplifying it further, I can say that QD and QQ, that is equal to 1 minus 1 by 2 minus 1 by 2, 0 under root 3 by 2 minus under root 3 by 2 into QA, QB and QC. So if we have the instantaneous values of the phases, we can find out their projection over the D and Q axis, and we can define a vector representing that three-phase system in this DQ plane. But this is calculated for one instant of time. At the other instant of time, the quantities along A axis, B axis and C axis will get changed, because this QAT is basically defined as, let's suppose this is a sinusoidal function varying with time. Then QBT, let's suppose this is sine of omega t minus 2 pi by 3, because phase B should be at the angle of 120 degree, either leading or lagging. So for the positive sequence, it is at angle minus 2 pi at the angle 2 pi by 3. And phase C can be written as sine of omega t minus 4 pi by 3. So at any instant of time, we can find out what is the QA, what is QB and what is QC, and those will be considered over here in this equation, right? And then we can find out the QD and QQ for that instant of time. So as we will be moving in the time, so this QD and QQ will be changing. So now let's assume that we have these sets of QAT, QBT and QCT, and let's see how your resultant will be represented in the DQ plane. Okay, so how I can find out that one? Let's find out Q net or the Q resultant. That will be equal to QAT into e raised power j0, if we assume theta is equal to 0, plus QBT e raised power j2 pi by 3 plus QCT e raised power j4 pi by 3. Okay, so now this is this QA is given by this one, so I am going to write sine of omega t into e raised power j 0, so that means cos of 0 plus sine of 0, so that is going to become 1. So this will remain sine of omega t, then plus, now taking the second term QBT is given as let's suppose sine of omega t sine of omega t minus 2 pi by 3 into e raised power j 2 pi by 3. So we have seen that is equal to minus 1 by 2 plus under root 3 by 2j. So now taking that value over here, directly I can write it like that, minus 1 by 2 plus under root 3 by 2j. Then taking QC is sine of omega t minus 4 pi by 3. So whatever is the value of this, it will be multiplied with minus 1 by 2 minus under root 3 by 2j. Okay, so now if I simplify this one, so I am just going to write down the end result. So this will be equal to 1.5 into sine of omega t minus 1.5 cos of omega t with j. Okay, so Q net, the net value will be given by this expression at one instant of time. When the time t will change, so sine and cosine terms will change and you will get some Q net value. So what this basically is representing? This is representing the equation of a circle. So with the variation of the time t, you will get a resultant vector, and that resultant vector will be rotating over the circle. So if I represent it over here, let's suppose this one is the d axis, this one is the q axis. At one instant of time, you will get some q net, that is at this point, and let's suppose this is at angle theta. At certain other instant of time, now as the time changes, theta is equal to omega t, your q net will be somewhere over here, because its magnitude is always 1.5 times the magnitude of the sine of omega t. Sine of omega t was our first phase. So magnitude of the d component is 1.5 times the magnitude of your phase. So as your theta will be varying, so q net will be changing its position, but its magnitude will be same, because if you write it in terms of if we take 1.5 common from here, so this is sine of omega t minus j cos of omega t, and this is basically representing the circle, right? So you will be moving over the circle having the radius 1.5 times the magnitude of the sine wave. Okay, so your resultant will be rotating over this circle. So basically we say that at any instant of time, this is a vector, and that is represented like this. So this is said to be the space vector. That's the representation of the three-phase system in the dq plane, and this dq plane is called the space vector plane. Okay, so the magnitude of the resultant vector is 3 by 2 times the magnitude of your phase. Now if I say that I have a three-phase motor, let's suppose this is phase A, this one is phase B, and this one is phase C, and all of these phases are being used to run a three-phase induction motor, and the power capacity of three-phase induction motor is 300 watt. So if it is a balanced system, 100 watt will be provided by this phase, 100 watt will be provided by this one, 100 watt will be provided by this one. So total power of the motor is three phases. All the phases will contribute equally. Now when we have translated this ABC system into DQ, so I can say that let's suppose now we have two phases which are supplying the power to this three-phase induction motor, and the power of the motor is constant, that is 300 watt. So this is now D phase, this is now Q phase. So what should be the power that should be provided by D? That should be 1.5 times the 100, means 150 watt should be provided by phase D and 150 watt should be provided by phase Q. Because basically if I look at the D and Q representation, so what you are going to get, you have basically sine wave over here representing the D axis. This one is the D axis variation, and that is the sinusoidal variation. And over the Q axis you have cosine waveform. So that is minus cos over here, so I should sketch it like this, negative of the cosine waveform. So basically we have the two sinusoidal functions in the DQ frame. Over here there is the sinusoidal representation, and along the Q there is the sinusoidal variation. Okay. So sinusoidal variation over the Q axis and the sinusoidal variation over the D axis. And if we sketch them together, if we plot them together, you will get the circle. Considering this sine over the x-axis, this sinusoidal waveform over the x-axis, and this cosine waveform over the y-axis, if you plot them, so you will be getting the circular representation. Okay. Now if you swap these two, sine function and the cosine function, so you will be getting a circle rotating in the opposite direction. Your space vector will be rotating in the opposite direction, and that you can get reversed by having by changing the sequence in the ABC system. If you swap any two phases over here, let's suppose you make this one phase C and this one phase B. So keeping the sign same over here, so you will be getting a circle rotating in the opposite direction. Okay, now if I say that I want to keep the power same, power equation same for the DQ frame of reference, so our voltage and current should remain same. But as you look over here, we are having the factor of 1.5. So if I divide it by 1.5, so we will be only left with this part of the equation, and in that we have the sine of omega t, and which was our phase A, this one. So both of them will be having the same thing. So the magnitude of the phase A will be equal to the magnitude of the phase D, provided we multiply this resultant vector with 2 by 3, or the we divide it with 1.5. Okay, so in order to keep the magnitude of the resultant same as that of your phase A, what we can do, we can divide D and Q component with the 1.5, or we can multiply it with 2 by 3. So QD and QQ now can be written as 2 by 3, 1 minus 1 by 2 minus 1 by 2, 0, under root 3 by 2 minus under root 3 by 2 into QA, QB and QC. These are the instantaneous values. So why I have added this 2 by 3? so that the magnitude of the phase A and the phase D remains same, so that now the power that will be measured after multiplying with 2 by 3 will be definitely reduced by 2 by 3. So what you will have to do to get net power, you will have to multiply it with 3 by 2, that means 1.5, to get the power 100 watts in the 3-phase system and 150 watt in each phase over here. So if we have the voltage and the current represented in the form of space vector, this 2 by 3 is commonly used to have the same magnitude of phase A and the phase D. Okay, so now I can represent this space vector, that is QD plus JQQ. I am going to call it space vector, right, or simply the Q, that is equal to 2 by 3 into QA, instantaneous value of that one, plus A into instantaneous value of QB, plus A square into instantaneous value of the phase C. So I have taken basically this equation, this one, and I'm going to call it this space vector, right? And the only difference is that we have multiplied it with 2 by 3 to keep the magnitude of phase A and phase D equal to each other. So this expression is the expression for the space vector and will be used onward for the explanation of the space vector PWM. So this is the final expression that we have obtained in discussion in this video. So any 3-phase quantity that is given to us, we can translate it into dq axis, right? So if we change the sequence, our representation will be affected. But how it will be affected? The direction of rotation will be changed. For one sequence it will be like that, and for the other sequence, if we swap 2 phases, the resultant will be rotating in the opposite direction. That's all from this video. We have represented the 3-phase system in the 2-dimensional plane, that is the space vector plane, dq frame of reference, and that is the stationary frame, and we have seen that how we can represent a 3-phase system into a 2-phase system. Okay, thank you.